This is a video to review thermodynamics, which is a key AP review topic, so make sure you pay attention and you take notes because some of these things are very key on the exam. First thing is the exam is using a new code word basically. They're starting to use thermodynamically favored instead of spontaneous. It means the same thing. So if you read thermodynamically favored, it means you think the same way that we thought of in class. It means spontaneous. Same idea. Spontaneous process is something that you can have happen without basically adding any energy versus a non-spontaneous process. In order to make it happen, you have to add some energy. Some key things. One fundamental thing, thermochemistry is built around a calorimeter. In chemistry, we use like a coffee cup calorimeter. We basically do that to prevent the heat loss, and there's always water. So if you see it on the exam, a calorimeter problem, the idea is, and this equation is provided for you in the booklet, here's the heat equation, you need to copy this down. Q is what we're solving for, which is heat is going to be in joules. M is going to be mass of the water, because when we're doing it in a calorimeter, we really focus on the mass of the water. Specific heat of water we know is 4.184 joules, and then finally the temperature change of the water. By measuring the temperature change of the water, we can figure out what happens with the reaction. The reality is we do everything in water. When we measure the amount of calories in a Big Mac, let's say, and they're trying to calculate it out, we do it in water because we know the specific heat of water. We can measure the volume, which is basically the mass in water, which allows us, by the temperature change, to figure out what happens to the water. And remember, what happens to the water is opposite of what happens to the reaction, so all we do is flip the sign. So one key thing they want you to do on the AP exam is they'll ask you how to find the heat of a reaction or to do it. So the first step is you find the Q for water. So ultimately, the first thing you're going to do is you'll find the Q for water. Once you find the Q for water, the second step is you're going to flip the sign. Why? Because what happens to the reaction is opposite of what happened to the water. And you're also going to divide by 1,000 because when they ask you for heat of a reaction, they're going to want it in kilojoules per mole. That's the units that they use, so copy that down. The third step is always just take your new kilojoules that you have and divide by moles, and it's the smallest moles of the reactant or whichever reactant they give you, because think about limiting reactant. It's the smallest number of moles of a reactant, and after that, when you do all that, you have the heat of a reaction. So those are the key 3 steps to finding the heat of a reaction, which is in kilojoules per mole. We do it in a coffee cup. We find our temperature using a thermometer. Boom. We have our specific heat, and we can check the mass of the water by basically measuring its volume, and we go from there. That's how to find the heat of a reaction. Now, heat can be used as a conversion factor. One thing I want you to be aware of is when you look at this equation, it is exothermic. How do I know it's exothermic? Because the H is negative. The other thing I want you to be aware of is the ratios. If you notice here, one of these is equal to negative 184.6. One of these is equal to negative 184.6, and 2 of those. So heat is a conversion factor. So if they give me 12.8 grams of H2, which you see them giving me right here, then I just take basically our first step is always to change grams of H2 to moles. Once I get to moles, then instead of the turkey, I use, remember the tofurkey? We say 1 mole of that is equal to negative 184.6. I can create a conversion factor to grid, calculate out, and it'll tell me how many grams of heat is released. The reason that I know it's released is because the sign is negative. So there is an example of heat being used as a conversion factor. Whatever they give you, convert to moles, and then use the heat value right there, basically the coefficient and the delta H, multiply it. I could ask you to do that tomorrow. In fact, I probably will. So take a look at that. There's your solution. Next thing, key thing that they ask a lot about is endo and exothermic, so we're going to do a little compare and contrast. In thermochemistry, we study the system. If we say something is exothermic, we say it has a negative sign. So on the exo side, it's negative. So exo is negative. We also know that energy is going out into the surroundings, and what that's going to feel like, the key thing you'd write down on that side, is it feels warm or hot. Why? Because if the energy is exiting, and this is your hand, right there, it would feel to us warm. So exothermic reactions feel warm. The other side of it is an endothermic reaction. Endo means heat is going in. So in this case, heat is going in. Endothermic is associated with a delta H sign of positive, and since energy is flowing in, it's going to feel cold to us. Key thing, a lot of times on the multiple choice, they will ask you, and I could ask you this tomorrow, is exothermic, the sign is negative, it feels warm if you're holding a beaker. Endothermic, delta H is positive, and it feels cold. So that's the key thing. So an exothermic reaction, energy is being released associated with a negative sign. The bonds actually are more stable as well. Endothermic reaction, energy is being absorbed. The new bonds would be less stable. Another key thing is to be able to spot it in a graph. When you look at a graph, an exothermic reaction, remember potential energy is always listed here on a reaction coordinate. This is like a normal reaction graph like this. Remember what's happening is this is the delta H value. Delta H can be found on the graph. It's the difference between the reactants and the products. But graphically, in exothermic reaction, the products are always lower than the reactants. That makes sense because delta H is declining. The value of energy is decreasing right there. Versus an endothermic reaction, the products are always going to be higher than the reactants. So again, the delta H can be found, the two differences between the difference between the line of reactants and the line of products, or the level. My delta H would be positive, and that is an endothermic reaction. All right, one of the things we do is we do reaction manipulation. So it says on there, manipulating reactions, there are two things you can do to change a reaction. We're allowed to flip it, and we're allowed to multiply or divide, and we do the same thing to delta H when we do Hell's law. So if you look, a lot of times it will give you a complete equation with the delta H value. That happens to be endothermic because it's positive, and I can manipulate the equation to find the delta H value for what this would be if it took this form. First thing I notice is Ag2S is on the left-hand side here, and now it is on the right-hand side. So whenever I flip a reaction, I flip the sign. So ultimately, I'm going to flip this over, which means I'm going to change it to negative 595.5 kilojoules. The other thing I notice is it goes from having a coefficient of 2 to having a coefficient of 1, or having a coefficient of 1/2, which means it had to have been divided by 4 in order to change it to 1/2. So the last thing I do mathematically is that we take negative 595.5 kilojoules divided by 4. So tomorrow on your video quiz, what I could do is I could give you a reaction and give you a different reaction and have you match it. Key thing to remember, flip the reaction, flip the sign, you multiply or divide, do the same thing to delta H, and you'll be fine. Next thing, second way we find delta H, or the first way we actually find delta H, it's listed on your handout. It says bonds broken, reactants minus bonds formed. This is the only one where it's reactants minus products. Everything else is products minus reactants. It's the key thing to write down. Your first step in the problem is draw the Lewis structure. So like this problem right here, where they gave us N2 plus 2H2 equals N2H4. My first step would be to draw the N2 Lewis structure, and then the H2 Lewis structure, and then arrow NH4, which is going to look something like that right there. I have that molecule right there. And then when I go to do bonds broken, bonds formed, I have a chart. They'll provide me a small chart on the AP exam. So what I'll do is I basically remember this. I take the bond energy from the table. So this is the bond energy from the table for each one. The stoichiometric coefficient from the equation, and the number of bonds in the molecule, multiply them all, and I get the energy. I do that for all the bonds broken, all the reactants. Then I do the same thing for all the products, subtract the two, and I get the delta H for the reaction. The biggest thing most people do is they forget the stoichiometric coefficient. So if I look right here, I'm going to do one of these. This molecule right here contains a nitrogen triple bond. So to break that, I look at my chart. That's going to be 946 in energy. So I would go 946. How many do I see? I see one triple bond in the molecule, so that's 1. And then finally, the stoichiometric coefficient in that case would be 1. So for this whole thing, it would be 946. If I went to do H2, HH single bond is going to be represented by 436. So then I go 436. There's one bond, but my stoichiometric coefficient on that is 2. So I'd multiply that by 2, and then you would end up with, what is that, 872. 872, and then that would be all my reactants are done now. So I'd add these together, do the exact same thing on the other side, and then subtract the 2, and I find delta H. The next way to find delta H, the second box there, is what you want to write down is products minus reactants using a table. Two key things you want to write in the box, or the biggest thing you want to remember, is elements have a delta HF value of 0 for all elements. This one's products minus reactants, so the key thing you want to write in your little note-taking box underneath there is we use products minus reactants. Delta elements are going to be equal to 0, and use the coefficients as well. This one you're going to use the coefficients to find delta H. You notice in the table, it's an HF table. I have HF values given to me. So I look at the HF values, and if I go over here, in this problem, if you notice, these are the values that are already on the table. They're already looked up. So when I go to calculate it, I just have to make sure I do products first. So I'm going to do the products. Then I'm going to subtract the reactants from the products. So I'm going to do this. 4 times negative 110 is going to be negative 442. So that would be negative 442. So I multiply 4 times that. 8 times 0. The reason why that's 0 is because that is elemental in form. So then that's just going to be 0. I'm done with the products. I sum those up. Then I do the exact same thing with the reactants. 3 times 74, 2 times that, 1 times that. Sum all that up, subtract it, and I find my delta H. The last way to find delta H is Hess's law of reaction flipping. They will give you a target reaction, and remember when I taught this, you have to find a compass. A compass is something that is in the target reaction, like I noticed CO here is a gas, is here and it's not anywhere else. So the fact that I know that CO is not anywhere else, O2 would be a bad compass because it's in both reactions. It's hard to figure out. So I see CO. First thing I know is I have to flip this reaction over, which is going to change the sign to that, make that positive. Second thing is I have to multiply that sucker by 2, and that's how I manipulate that. The bottom reaction, CH4 as a gas, will be my compass. It's on the correct side, so I don't flip it, but notice the coefficient is 2 in the target, so I would come over here and multiply that by 2. And all Hess's law states is that if you do all that, you get your overall reaction, you add it all together, you get the delta H for the whole reaction. So those are the 3 ways to find delta H. Okay, entropy. Entropy is disorder. So entropy, when we talk about disorder, is the measure of disorder in a system. Okay, so it's a measure of order in a disorder in a system. Key thing you want to know is that basically if a process is spontaneous or thermodynamically favorable in one direction, it would be non-spontaneous or non-favorable in the other direction. Here we go. This is listed on your notes. Key thing to remember, if H is positive, we say entropy is increasing and it favors being spontaneous or thermodynamically favored. If S is negative, we say entropy is decreasing. We say it tends to go towards a non-spontaneous reaction. The first thing we always use is the SLG rule if they're not having us calculate it. The SLG rule means that solids are more organized. Then if you have liquids or something that's aqueous, it's less organized. And then if you go from L to G, it becomes more disorganized. So as you go this direction, delta S or entropy is increasing this direction. If you go the other way, it decreases. So delta S going the other way would be negative. So that's what we mean by doing by inspection. The other key thing that you have to remember is if they're all gases, you can't use the SLG rule. So what do you remember? Going left to right, if moles, more moles, left to right, more entropy. Easy way to remember it. More moles, more S. Less moles, less S. You notice here I only have 1 mole on this side, 2 moles on this side, so I would say my delta S value for this would be positive because of that. So they always, in the multiple choice section, will have you do entropy by inspection. So if you look here, here's an example. I have L and G. Using the SLG rule, I know that entropy is increasing because I'm going from a liquid to a solid. If I notice here, gas and a gas, so I look at the number of moles. 1 mole on this side, 2 moles on this side. Entropy is increasing, so delta S is positive. If I look here, gas, 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 gas. If you notice I have 2 moles on the left and 2 moles on the right, we would say no change. So you can't, the only way you can figure that out is by calculation. The last one is solid to a solid, which is kind of a wash. Nothing really happens, but then I have solid going to a gas as well. So I would say the entropy is increasing in this reaction, so delta S is positive. All right, one thing we can do is we can calculate delta S. So when we go to calculate delta S, by calculation, what we do is you sum the products using the stoichiometric coefficient, sum the reactants, and then subtract them. It's very similar to delta H. You're going to use the coefficients and all that. The one key thing that you need to keep in mind is everything has an S value. So everything has an S. Has an S value. So when you go to do that, it's not like delta H where elements are 0. You notice here O2 is an element and O2 has an entropy value. So you plug those in, again using the coefficients. It's exactly the same thing that we did. And you calculate S. Now, and here you see the calculation. You total it up, subtract products minus reactants. Free energy is the ultimate thing we're looking at. If delta G is negative, we say it's spontaneous, or now we could say it's thermodynamically favored or favorable. Since that's new terminology that we use. If it is positive, we say it's non-spontaneous, and if it's at equilibrium, we say it's 0. Key thing you need to memorize. This is the grid that we filled in. You're going to need to fill this in again. I think I put it on the wrong page. This is on the next page. You have to flip over. If S is positive and H is negative, we say it's always spontaneous. So if you find S positive and H negative, it's always spontaneous. If S is negative and H is positive, it's never spontaneous. And then the only time you really have to think or really apply temperature, temperature only comes into play when the signs are the same. Notice how it's positive. Positive means it's spontaneous at high temperatures. Think plus plus on a thermometer. High temperature, minus minus on a thermometer. So if the signs are the same, then temperature matters. So this would only be spontaneous at low temperatures. If you look here, here's an example of applying it. My delta H, they're telling me it's exothermic, so it would feel hot. A lot of times they just use the terminology hot on the AP exam, but they're giving you the negative delta H here. And delta S for this one goes, it's GGG, goes from 3 to 1 mole. So my delta S value is going to be negative. So this is negative and this is negative. Using the table, it would be spontaneous at low temps. If I look at this one, see how my delta H is positive? This would feel cold because whenever delta H is positive, it feels cold. So then when I look at my delta H is positive, my S goes from 1 mole to 2 moles. So my S is positive. Again, they have the same sign, so temperature matters. So this is going to be favorable at high temps. Thermodynamically favorable at high temperatures. All right, Gibbs free energy, we do the calculation. It's called going home to supper. Key notation you need to make there, I gave you a box, is you have to remember to change your S units. Delta S is in joules, so you have to basically divide by 1,000 to change it into kilojoules. That's the most common mistake people make on the exam. Otherwise, you plug in your H, plug in your T, adjust your units for S, and you solve for delta G in kilojoules. If you notice, here's an example. They give you H values, formation, and S values. This is 0 and 0. It's elemental, so you do the math. Everything has an S value. So what ultimately you would do is do products minus reactants. I get this value. Products minus reactants for S. Notice it's in kilojoules. So I can't say it's negative 198.9. It has to be changed to negative 0.1989. Notice it's adjusted. Make sure you note that. You always have to adjust your S when finding delta G. Once you find delta G, if it's positive, it's thermodynamically favored. If it's negative, it's thermodynamically favored or spontaneous. If it's positive, it's non-spontaneous or not favored. Delta G can be done the exact same way we do S and H. They very rarely ask you, but if they did, delta G values for elements are 0. So then you just basically pop in the info that they give you and you solve for it that way. Last thing we really need to focus on, there's a relationship between equilibrium and delta G. I gave you a box because I wanted you to label this. Label in the box that must be delta G when you're solving for KEQ must be changed to joules. Since R is not the gas R, but 8.31, that's the other notation you want to make in that box. Two notations, R is 8.31. Delta G has to be changed to joules in order, because we don't change the units of a constant to solve for KEQ. Relationships between delta G and KEQ. If delta G is greater than 1, we say it's non-spontaneous, which means, or non-favorable, which means KEQ is going to be less than 1. If delta G is negative, we say KEQ is greater than 1, and if delta G is 0, KEQ is 0. One thing I just remembered I left off that you need to copy on the side of that is this. Whenever you need to find the temperature at which something becomes spontaneous, it's equal to delta H over delta S. Write this down. That's how you find the temperature at which something becomes favorable or spontaneous. I'll use the favored. Temp favored. That's the temperature at which the reaction becomes favorable. You just stack H over S. When you divide H over S, just make sure the units of S are correct. You can find the temperature at which it becomes spontaneous. All right? That's a complete review of thermodynamics. Really, just remember this. There's 3 ways to find delta H. Bond's broken. That's the only one that's reactants minus products. Hess's law is reaction flipping, and then this is using the table. All those can give us a delta H. Delta S can be found by only products minus reactants. Be sure to convert to kilojoules. Drop that in there. You get your delta G value. After you get your delta G value, you can solve for equilibrium. All right? Have a good day.